Io vado avanti con questo, ma se sto lontana da qua, ci provo. Yeah, it's not the last one, sorry. My reason mainly is because they are really a good platform to study exciton that are, I mean, the main topic of my research in the last year. And so due to the strong quantum confinement effect, to the strong dielectric confinement, this material generally have very strongly bound exciton. And these exciton are not important only from theoretical point of view, but also from applicative point of view. So there are many work that demonstrate that 2D material can be useful for light emission, also for electronic device that use the fact that they are quantum material, but also in photovoltaic application. The main interest is the fact that these exciton are stable at room temperature, something that is not so usual in normal semiconducting material, and also the fact that this material are really prone to the fact that this exciton can be changed with chemical composition, with doping, with strain, and with electric field. So there are many ways that people can play with exciton and in general with electrical properties. So what I want to discuss with you is some results about different classes of material. First, I want to say something about the transition metal dichalcogenide that have different interests like LED, photodetector, in electronics, spintronics, and also in solar cell. And then I want to speak about a new material that is a new family discovered by theoreticians with machine learning or something like that. That is a new family that has some advantages. Actually, from experimental point of view, they've not been grown already, only one of this family, but they are very interesting. I want to say something also for Giorgio, to remember something about these 2D polymer material that are very interesting. We did some activity together in Lazio, Regione Lazio project, and here we speak about excitonic properties. And finally, I want to discuss for Aldo, that is not here, but also for you, something about 2D perovskite, that are a class of material that are not 2D really, but since there is this organic part, they behave like 2D materials. Being a theoretician, all the results that I will discuss are related to some calculation. So all the results that I will discuss is based on calculation starting from density functional theory that I think you know very well. Is the master DFT, the master Ab-initio theory for a physicist that allow to obtain very good properties related to geometry and structural properties of material, but also about electronic properties, but sometimes many quantity related to electronic properties are not in agreement with experimental data. There is the underestimation of the gap. And so what we do with Vergata, also other people here, this expert, Daniele and Marco also do this kind of calculation. What we do is try to correct the electronic gap of DFT that are obtained from Kohn-Sham equation with something that is called the GW method. That means that we correct in a perturbative way the energy that we obtain from DFT. So we do a DFT calculation, and as post-processing is very computational heavy. It's not, something that we can do without a supercomputer, unfortunately, for many materials. We are able to correct the electronic gap and to compare the electronic gap with the transport gap that you can obtain in the experiment with the photoemission, inverse photoemission, or scanner internal spectroscopy. And then to obtain exciton, so to describe, for instance, absorption spectra or something like that, also to understand if the material, there are bright or dark exciton that enter in the optoelectronic properties, also to calculate in some way radiative lifetime. What we do is to solve a two-particle equation that is called the Bethe-Salpeter equation, that, as you can see, is, this is really simplified, but here you see that there are two Hamiltonian that are the single particle Hamiltonian of the electron of the hole, and then we have a term that is what we call coupling, that is quite complicated. This is only simplified. That means the electron-hole interaction. So the fact that the electron and hole in the material are coupled by the Coulomb interaction, screened Coulomb interaction in the material. And so, as you can see, when we describe the absorption, for instance, you have that the absorption as in the delta function that exprime the conservation of energy, not the energy of the Kohn-Sham or the GW, but the excitonic energy that we obtain solving this two-particle equation. So they are redshifted typically with respect to the electronic gap in many materials. And also, as you can see, the intensity of the peak change with respect to in single particle approach, because there is this term that is called the excitonic eigenvector here, in this Hamiltonian, that they normalize the intensity of the peak. So this term is very important to obtain also not only the position of the peak, but also the intensity of the peak and compare with the experiment. So with this approach, normally what we do is try to be in some sense predictive with respect to the experiment, so be able not only to describe ground state properties, but also spectral properties. And this is the example that is quite old now, but is the comparison of transition, of transition metal dechalcogenide died. Dark state. Okay. The comparison of theory and experiment for transition metal dechalcogenide monolayer. This is molybdenum disulfide, and this is tungsten disulfide. As you can see, this is well known now, but we are able to interpret the position of the peak as excitonic peak, that are the A and B peak of this material, for instance, but also to know that below the bright peak that are entering the optical spectra, there are also states that are spin forbidden in this material that are called dark states. So we are able to describe direct exciton. Actually, it's possible to describe also finite momentum exciton, but do not enter generally in the absorption spectra. So in this way, starting from the Bethe-Salpeter equation, it's also possible to calculate the radiative lifetime of this material and compare the experimental and theoretical data, and the agreement is quite nice, reasonable at least, from Ab-initio. So what we did with other people is start, for instance, from molybdenum disulfide monolayer and try to see how the optical properties, also the electronic properties, change, including, for instance, in the simulation, not the pristine material, but the presence of sulfur vacancies, because in this material, sulfur vacancies are very frequent. And then we asked ourselves, what happens if I try to fill this vacancy, sulfur vacancy that are very frequent experimentally, with different kind of dopant. And so, as you can see, the situation here is the pristine case with valence and conduction. This is, for instance, the case with sulfur vacancies, where you can see that we have an in-gap state between the valence and conduction, and different kind of dopant. What I want to show you here is the fact that when we have the sulfur vacancies, there is this peak in gap states. But for instance, when we consider oxygen or molecular oxygen, the in-gap state completely disappear here, and also the orange. So what we did was, for few cases, try to calculate the optical properties of these cases, and as you can see, the optical spectrum that we obtain, in the case of pristine is the normal peak with A and B. When we consider sulfur vacancies, there is this in-gap state, so exciton related to vacancies, while when we consider vacancies with oxygen or molecular oxygen, the in-gap states disappear. And considering, so this is in agreement with experimental data, in the sense that for tungsten disulfide, they actually demonstrated the presence of this in-gap state here. And but what we did, while in the case of oxygen, people discussed the fact that the luminescence of this material increases really much when there is an oxygen ambient condition, and so the in-gap state disappear, and actually the luminescence of the intrinsic exciton should be very strong. From our theoretical calculation, what we understood is the fact that this is true. So there are, what happened? I don't know what I'm doing with this, sorry. No, okay. So, as you can see, the excitonic wave function that is here, in the case of pristine, is this one. So here, this situation represents the whole probability when the electron is fixed in a given position, and this is in the layer of material. And as you can see, the situation is different in the case of pristine. In the case of sulfur vacancies, very, very localized in the sulfur vacancies, while when we put oxygen, return exactly like in the case of pristine, while when we put O2, is again localized. And also the radiative lifetimes seems in agreement only when we put oxygen. So the idea is that atomic oxygen, be on the same column of the periodic table, actually with the same number of oxidation like sulfur, is replacing in all the way the presence of glycogen. Okay. So, and this is what I want to tell about this. Another case that I want to discuss, always on transition metal dichalcogenide, is how we can understand and interpret the experimental data. For instance, this is the case of bilayer of tungsten diselenide. And in this case, people know that when they move from monolayer to bilayer and rotating the angle of one layer on top of the other, also the optical spectra or the energy loss spectra change. So it means that the excitonic properties, the excitonic peak change related to the angle. So the idea is try to understand how this change in the optical spectra, in the energy loss spectra, is related to the excitonic properties. These are experimental data of material in the case of monolayer, in the case of normal stacking, that is A prime stacking, and different angle of one layer on top of the other. This experimental data has been renormalized in order to have the A exciton at the same energy, so at 0. And as you can see, what we can observe from this experimental data is the fact that A and B exciton are more or less at the same position with respect to the 0, while it is observed a blue shift of C and D peak that are the different excitons. So what we did in collaboration with this group is try to understand from calculation of the monolayer and bilayer the origin of this peak. And as you can see here, the A and B are localized. This is the Brillouin zone, and the blue here tell you which are the point in the Brillouin zone that participate to the exciton, let's say. And so A and B are very localized in the K point of the Brillouin zone, while as you can see, the C and D are more spread in other point of the Brillouin zone, especially in the case, both in the case of monolayer and in the case of bilayer. So the idea is that this behavior actually is due to the fact that the exciton C and D are related to different regions of the Brillouin zone. And so to understand much better this, what we did is not only do the simulation of the excitonic properties for the monolayer and bilayer in the normal 1x1 cell, but really do calculation of the supercell and then do the unfolding of the bond structure in the 1x1 cell. And as you can see here, what we observe is the fact that the direct gap at K, that is this one here, remain almost fixed depending from the angle, while the indirect gap, minimum gap, here change depending from the angle. There is a maximum and then goes down. And so we try to understand this exactly related to the fact that the C and D peak actually are due to this region along the gamma K direction that change really much, especially in the conduction. So this explains the fact that the peak in some sense move with the angle. So the idea is that when you have the C and D peak that move blue shift, you are in a situation where the two layers do not interact too much. So you are going toward a situation where, due to the angle, the two layers do not interact. So from the shift of the peak, people generally what they do, they see the Raman peak. But in principle, you can use this kind of analysis, energy loss, and understand in terms of the position of this peak, if the layer are, I mean, also you can do other kind of analysis, but which is the kind of stacking, because generally, depending from the angle, you can have a different contribution from A prime, A, B, and other kind of stacking. Okay.
How do you set the boundary condition for the tilted layer?
Sorry?
How do you set the boundary condition for
in basis of strain? I mean, we minimize the strain. The boundary condition is, I mean, the strain is not a wave code. We did this part with the not localized but set code.
Okay.
So it's very big simulation cell. We don't do simulation.
The data of the AC you showed is in the optical limit, right?
Yes, in the optical limit. Yes,
So you could
sure.
monitor
The direct. In principle, the direct. They can do also experiment with finite momentum.
You could monitor the onset directly inside the CP.
Exactly. So let me go down because okay. So another example that I want to report is the fact that, as I mentioned before, this material in general, 2D material, are very prone to the fact that the optical properties, the electronic properties change really much with any perturbation. And so not only doping, but also strain. So this is another work done in collaboration with a theoretical group I don't remember where what we did was to do simulation of another bilayer, hetero bilayer this time, not tungsten diselenide, but tungsten diselenide, molybdenum diselenide. This kind of material is interesting because they have a type 2 interface of the band structure, so means that they form interlayer exciton that are very interesting because you can have a separation. So you have the electron in one layer and the hole in the other layer. And so this material are often used as very thin, prototypical material to do separation of the exciton, to do charge transfer or whatever it is. So here the idea is that considering this hetero bilayer in the normal A-gram stacking, we want to analyze how, again, the optical properties change with strain. By strain means tensile strain from 0 to 5%. And as you can see, the optical spectra change a lot. So we have the typical A and the A peak of the two monolayer that here we call X2 and X3. And we have also very dark exciton that are spin forbidden interlayer exciton. So the hole is in one layer and the electron is in the other layer that are dark. But what you can see in any case is that changing the strain, the spectra are really different. So this means that, again, what experimentally you can measure can really depend from the sample because you can have exciton that change not only in terms, so X2 that is a molybdenum tungsten here, but also you can have the opposite, so different character, and also the position of the peak change a lot. Again, you can, with strain, analyze the origin of this peak. Again, here the black that you see here tell us that, for instance, this exciton here is an interlayer exciton because one is blue, that means in one layer, that is tungsten. The other is molybdenum, that is where the electron goes. So the exciton is completely interlayer, but as you can see, analyzing all these three main exciton, also the character change and also the gap comes from indirect to direct. So the situation is really, depends really from the kind of sample that you are eventually growing. And also another information that we found is that with strain, increasing the strain, the intralayer exciton are more dependent than interlayer exciton. So the reduction is linear in all the cases, but the linear coefficient is different. Okay. One last point that I want to discuss about TMD, then I move to another topic. Let me know which is the time so I can skip argument because I don't want to annoy too much. Is the fact that in this class of material, as I mentioned, these heterobilayer are interesting for the fact that there are these interlayer exciton. That means that you can excite with light and the electron and hole go in one of the two layers, so they can be separated, like a type 2 interface of the band structure. But what we asked recently with Olivia and Alessandro Pecchia from CNR also is the fact that how again, the optical spectra change if we consider the the presence of sulfur vacancies, but also of dopant. So we did exactly the same exercise that we did before, considering oxygen on top of the sulfur vacancies, or for instance carbon atoms that is also very frequent in the experimental condition. And as you can see again, what we observe is the fact that when we put oxygen, the spectra recover exactly the situation where there is not sulfur vacancies, so the in-gap state are eliminated, while when we consider, for instance, carbon on top of these sulfur vacancies, what we found is that we have activated the excitonic peak below the gap. So there are very, intense peak below the gap that are due to the presence of these states due to the dopant. So it's really possible, in principle, to modulate the optical properties of this material. Okay, how many minutes? So I skip
10 minutes.
10 minutes. So I skip everything about this. I go to, because this is not interesting for you, what I want to discuss for Giorgio, and maybe from other of you, because we have still to write a manuscript, is the idea that you have the possibility to study not only to the material that are grown, exfoliating, but also you can self-assemble to the material starting from molecules. And this is an activity that I started, since we have this collaboration with him. So we did the calculation actually of the transport properties, but we are not ready to show results here. Instead of some results not yet published, but I think that they are very interesting. The idea is that they did, this class of material are obtained from what are called the triangulene, and then this triangulene molecule, these theoretical people here show that you can have different material with the properties that change from metals to semi-metal to semiconductor, depending if you consider molecules with boron or with nitrogen on top, and also if you have bridge atoms that are in this way, or with carbon, or in this way. So you can really modulate different properties. It's a nice manuscript. What is interesting when we started the collaboration is the fact that in many cases this material that have a Kagome structure have Dirac cone and flat band. So means that you have properties of material that are like a semi-metal, like graphene, but at the same time you have flat bands that should remember the fact that you have a material with electrons that can have a strong correlation. Generally, when the bands are very flat, means that you can have material with strong correlation. So the idea you can have both kind of properties. And as I show you, actually Giorgio and collaborators some time ago did really realize this material growing on gold 111, and they demonstrate the presence in this case with the nitrogen with bands that really have are semiconductor in this case, these triangular molecules, and with Dirac cone both in the valence and in the conduction. And interesting, if you, again, with dopant or electric field are able to dope the material and arrive at the Dirac cone, you can have a very high mobility, so like in the case of graphene. So this is very interesting. And what we did is actually try to understand again the optical properties of this material, not yet measured. I think that is not very easy to measure, because what we did was calculate the freestanding layer of triangular molecules without any supporting material. I have to say, honestly, that when we will do any kind of experiment, probably with gold, the situation that I described here is not probably maintained, because the excitonic properties change a lot depending on the substrate. So what we again observe in this case is the fact that the electronic gap that you see here in the DFT calculation and GW change completely. So the gap is normalized really much, means that DFT is not able to reproduce the electronic gap. And interesting also in this case, we played considering the case of one layer with nitrogen and one layer with boron. try to understand if possibly in an experiment we are able to build up a monolayer of one material, another monolayer of the other material, you can have which kind of semiconductor. And again, here we discovered that it's possible to have type 2 interface, so indirect exciton in one layer. I don't know how much is it easy, the experimental realization, but let me show you the optical spectra. Again, what we observe is the fact that also in this case, the excitonic properties are very, very important in the sense that we found exciton that are bound more than 2 eV in the freestanding case. And also the interesting things for this organic class of material is the fact that singlet and triplet exciton are very much split. This is something interesting for exciton fission experimentally. And again, as I mentioned, we have indirect exciton, so electron in one layer and all in the other. What I think is very interesting that should be investigated more, I hope, we can do some experiment, is the fact that in this material, these are 3 kinds of triangulum family with the nitrogen and different bridges. What we observe is the fact that the first exciton are due to bands that present direct cone, like here, but also flat bands, like here, for instance. So the idea, why I mentioned this, because some people before us mentioned this class of material without nitrogen, but are simple carbon, can be used as template to see and observe excitonic insulator transition. So they seems very interesting for some fundamental reason like that. And I think it should be nice to, if it is possible, to measure this kind of properties. Okay, let me skip for the last 10 minutes to perovskite. I hope Aldo was here, but it's not okay. So this is something that I don't have to tell you too much because there are many authors here. So the idea is that we use the same kind of framework to study the excitonic properties of 2D layered material. That means perovskite, for instance, which is the difference. That now we have quantum well, actually they are not really 2D, but since there is this organic part, generally the organic part is behave like the electric screening only. So the organic part generally do not enter in the main low energy excitonic peak. And for instance, this is a work that we did some years ago with Daniele and collaborator, where we calculated the optical spectrum, actually measured the time resolved absorption spectra, but they asked us to interpret the experimental feature, and from the analysis of the normal linear spectrum, what we were able to demonstrate was the fact that the first peak was due to the first 1s exciton, while the second peak that we calculated was due to the 2s excitonic series. This is something that experiment and theory seems to compare well in this analysis, and also we were able to understand that the excitonic binding energy is quite high in this material. Also, another lateral analysis was the fact that with this kind of analysis, as I mentioned, we are not only able to see the peak in the theory, but also to analyze the fine structure of exciton. For instance, in the case of perovskite, there was a lot of discussion, say, about the fact that from KP theory, group theory, the people mentioned the fact that the first peak was out of plane for symmetry rule, while actually from our calculation the first peak is dark, like in the symmetry theory, the group theory, but the first bright peak, so this one, is in plane polarization, while there was a lot of discussion until this manuscript, and actually this seems a general feature of this kind of perovskite. So the first bright exciton is out of plane, not in plane, not out of plane as symmetry theory analysis mentioned. the last part is related to some, again, work that we have done in collaboration with experimentalists related always to layered perovskite. But what we did here was try to analyze the difference of, again, perovskite like this with lead, but also with the tin. Why this? Because experimental people try to grow and characterize this kind of material because lead is toxic and also because the efficiency is not very high in the photoluminescence. So the idea, we consider this with this organic molecule that is phenylethylammonium, that is an aromatic molecule. And we look at the difference, and here again is the comparison with the experiment. As you can see, which is the main difference, that in the case of lead, there is the first exciton that is 1s, like before. The second peak is 2s, okay, experiment and theory. I shifted my theoretical calculation, then we can discuss about the position, but okay. Beyond the shift, the main point that we understood here is the fact that the second peak in the case of tin is very, very bright, different. So the experimentalist asked, why is so bright? Is the second 2s or is another origin? So what we understood, the experiment and theory do not compare very well, but I mean, we can discuss later, but we understood the origin of this. So the idea is the fact that in the case of lead, as you can see here, the main exciton is due to transition from top valence to bottom conduction. And then you have not only the 1s, but you have also the 2s of the excitonic series from this transition. While in the case of tin, the first exciton that is very intense is due to transition from here to here, while the second peak is due to transition from here to the second unoccupied bands. That is due to the fact that in the case of tin, the conduction is due to tin. The spin orbit is very small with respect to lead, so the states are nearest, and the transition is allowed. So in the message is that in the case of tin, the second peak is due to the higher transition. Is a new exciton, first exciton, 1x exciton, and another series, so completely different. And this influences also the dynamics because they did measurement of transient absorption, and they found a different radiative lifetime, and they interpreted this, in this way. I finish. Just to give you an idea, what we did more recently with Giacomo and other people was to go considering other organic material, because the idea is that phenylethylammonium is, it's good but not so stable. With this thiophenylammonium, people say that this layered material are energetically more stable, and because they found an efficiency in the external quantum efficiency of about 20% in the luminescence. So the idea is to try to understand again the excitonic properties. As you can see again, the excitonic properties with the beta salpeter, so excitonic included, agree very well with the experiment, while if you consider only GW, no. And again, in the case of lead, the transition are due to the top valence bottom conduction, while if you do, I'm confused, if you do the same calculation for the case of tin again, same tin and lead, you find again the same phenomenology. So the first exciton is 1s, while the second exciton is due to transition to the second bands. So it seems that independently from the organic material, the behavior of the exciton is related to the fact that the spin orbit change the splitting in the conduction. And I finish. Now here, just to tell you that what we are doing now is try to understand if in all this material that I mentioned up to now, all the transitions are due actually to the inorganic part. So the organic part play only the role in the screening. So the idea is, and this means that this material is very good in principle for luminescence, but not for photovoltaic cell, let's say. they are bound excitons, so they, in this case are not very good, but people try to understand if changing the organic material, there is the possibility to have, again, a type 2 exciton, so electron in one material and the hole in the organic part or the opposite. So chemists try to change the organic part. And what they did, for instance, is try to use PRN. In this case, what we observe is, this is very recent, still we have to work on it, but the idea is that in this case, the same organic like before with lead, but with pyrene, as you can see, the valence is in the organic, while the conduction is in the inorganic part. So means that when you excite with light, you have exciton that are type 2, let's say, interlayer exciton like before, charge transfer exciton, how you can speak. And also the optical spectra is quite complex in the sense that what we calculated, no experiment until now, we have exciton that are a mix, the nature, so from pyrene to lead inorganic part, lead, pyrene inorganic, so very complex structure. But again, the idea is that if you change organic and you go in a molecule that have a pi, electron, quite delocalized, this is very big molecule with respect to the other, you can have this kind of phenomena. And the last one, just to show you, this is instead one comparison where there is experiment. This is another case where people here suggested recently, some years ago, that considering another molecule, but this time not with iodine, but with chlorine, you can have type 2 interface, so valence in the inorganic and conduction in the organic part, like this. This is work done by experimentalists and theoreticians. They did the FLT and not GW. So what we did was repeat the calculation at the DFT and GW and beta salpeter level. Actually not GW, we did the shift. But here, as I can show you, is the fact that we are able to interpret the experimental data by the fact that it's true that is type 2, but our calculation is completely opposite to the other theoretician. While they have the top valence in the inorganic part and the bottom in the organic, we found exactly the opposite. So it's type 2, but with the top valence in the tetrazine, while the organic part play a role in the conduction. But the experiment is nice, and also, again, we have, in this case, dark charge transfer exciton. So the idea is that if you play, and people seems to also prove experimentally this, that you can have charge transfer, and so you can increase transport outside the plane of the inorganic material, changing the organic part. This is the idea. And so I finish. So, I hope to give you an overview of what we can do. This is only a small part. Actually, there are much more on that. What I used is mainly this code that is Yambo. Daniele Zia is one of the biggest developer with Andrea Marini, that is also, is the main developer originally of this code, but now is quite strong. What is important probably also for you is the fact that in many materials, in perovskite, there is also, but also in 2D materials, there is a strong importance to understand the dynamics. That is something that we didn't do, but it's very complicated, but there is an attempt to do that. And also to include the exciton phonon contribution to the optical spectra, because clearly in many materials, especially for instance in the case of thin perovskite, has been demonstrated the exciton phonon is very important. So these are something that has been developed recently in Yambo, and probably also in other code, Ab-initio code, that can be used by theoreticians and other to do, I mean, comparison with experimental data. So here, I mean, all the people that more or less, was involved in all the work that I described, and okay, that's it. So, ok, giusto, le domande. Aiuto.
Time for question. Giuseppe.
Dimmi.
Hi, thank you for your various talk. I have just a general question about how the perovskite, dimensional perovskite have type 1 and type 2 interfaces with the organic constituents. Because the point is that the general literature is quite a mess about this topic. You can find out for the same material that there are type 1, type 2, and which is I don't know, a rule of thumb, something like this.
I don't know. I don't have a question. And this is something that I ask also myself. Probably we should find some general rule. But up to now, I don't have a question. I mean, I don't have an answer. The idea is that from theoretical point of view, as I mentioned, if you do calculation in DFT using exchange correlation function that normally we use, like PB, probably you can have different results if you include the more refined functional. If you do GW, you can obtain another results, and if you do beta-salpeter, even another. So also theoretically, it's not very easy, depending from the kind of simulation. Since exciton are very, very important, you have to go beyond DFT in this kind of material. This is my impression. So any calculation that you do in DFT can be, different if you use a different function. So in any case, from what I've seen recently, people is really trying to grow perovskite with different organic molecule, and the idea is that, from what I understood, all the time that we have molecules that are aromatic molecule, not aliphatic, this is generally better to obtain type 2. For instance, in the MRS, I found people that speak about parto, I don't remember, very complex molecule. So there are different classes, violen, violen, I don't remember the name because so, but I think that is possible. The problem is that you must have very good chemists that grow. It is not very easy.
Question or comment. If you may have some gain in having an indirect exciton, partially indirect exciton, you pay the price of a lower matrix element for the absorption.
Yeah, absolutely.
So you,
in
the end.
No, this is true. This is true even if in this case that I show you seems that the indirect exciton, since there is a strong mixing, they are not nor in one or in the other material, they are in both. So they are not completely dark. If you see in the optical spectrum that I've shown before, there are peaks that are indirect, but with the oscillator strength that is not zero. So this is the idea, but you have to play with molecules, with different molecules to obtain this.
Related to that question, if you're thinking about it from a dynamical point of view, if you excite one of the higher energy excitons, which are localized in one layer, will they eventually evolve or get trapped into the charge separated exciton?
Yeah, this is why, for the perovskite, I don't know. For the TMD, this is what people observed. Yeah. This is, they observe this. You excite a higher energy, and they go in the indirect, and they see. It's true that in the absorption you don't see them, but in the luminescence you see the pictures.
You see, but they are weak.
Yeah, they are weak clearly. But
from luminescence, they are weak.
Yeah, sure. But again, in this perovskite that I studied, they seem indirect, but not completely dark, like in the case of TMD, where they are dark.
I have a question about the last part of your talk. So, in the recent past, last year, there was born a lot of literature about the possibility to excite a bidimensional, quasi-bidimensional perovskite exciting also the spacer. It is quite surprising. I mean, in general, the experiments was not so, convincing about the possibility to have seen that you have the separation. So the system is like an organic heterojunction. So you have to treat this like this because in principle you have to excite the system and separate the charge. You mean that the localized of aromatic ring is completely in the valence band, more or less. So it's present in the valence band because if you have to
depend from the molecule. I mean, you can have in the valence or in the conduction, no? For the two cases that I show is the opposite.
In general, the result you show for,
no, I mean,
for lead and tin, changing the spacer, you obtain more or less the same result. And this is reasonable because the spacer is more or less inert. Okay, so you use different layer, different spacer with respect to the chemical stability, to the separation, aliphatic or not, so the layer are close or not. Okay? In this way, you can obtain, a more bidimensional system. And changing the spacer, you obtain, in fact, more or less the same spectrum, the same result. So I didn't, realize how the spacer and the aromatic part of the spacer can be put, can interact with lead or tin.
If you analyze, if you analyze the bond structure, what you find is that in general in this material, the region in the valence near the gap is due to the inorganic. But if you go down, you find states that are in the organic part. So if you have to go down in the valence, and as generally in the conduction. So if you go up, you find states that are due to the organic. The point is that in the last two cases that I mentioned, triazine and the other molecule, happen the opposite. So the valence of the organic part goes up, or the conduction of the organic part goes down. So they are aligned in a different way. But if you go to see the bond structure, you see that they are localized in the two components. So they are, generally, you don't see experimentally because probably you excite from states. You have to excite very deep.
Okay.
And probably you will find it. Also in the case of phenetyl ammonium.
Okay, this is
you
access from the, the inner valence band.
No, they are.
Other questions?
Thank you for the seminar. And so in the organic semiconductor, you suppose in the calculation that is crystal. So a real solar cell is amorphous. So you mix in the pot.
I think that if you are, the idea is which is the difference.
Which is the difference? Because so in your crystal, there is clearly a conduction band.
Yeah.
In the amorphous, there is something that is related to an affinity band that is related only on the interaction between molecules.
No, I think, the idea from what I understood in the literature, if you have something that is crystalline, the efficiency improves.
Yes.
So this is the idea. From theoretical point of view, we didn't do any kind of calculation with amorphous. We avoid as much as possible.
But do you think that the mechanism would be different?
Yeah,
because
I think yes.
In the amorphous,
yes.
there is no real.
No. I think yes, it should be different. Maybe something like more hopping, probably. Something different. Here we assume that the bond structure is completely different.
Thanks.
Okay, Maurizia, did you try to include in your unit cells some defects in order to go into the direction of the amorphous?
Which material? Any?
Stefano.
Okay. In the case of perovskite, no, because the simulation, I didn't mention all the technicality, but these are not at all obvious. For instance, in the first case, what we did was actually completely, calculate the structure, completely took out the organic part, put cesium to saturate needed also in the calculation. We realized that the mass structure near the region that we are interested in was okay, and we did the calculation with cesium because the number of atoms were too big. And also in this last simulation, what I did, the experimental theory is very nice, but I shifted everything of 0.2, 0.3V because the agreement is not good for a lot of computational problem that I'm not able to, to have this. To include the defect, for instance, in the case of TMDs, yes, we did, we include the defect in the sense that we consider the prevalence of vacancies, but again, when you do simulation, you assume that the defect is in one position, and you replicate, or you create something that is of with defect, and you still do it this way. So defect kite with part, because if you do simulation, that this is something tricky, because for instance, in the case of phonetic ammonia, we fight for 1 year with the reviewer saying, no, your calculation are wrong because you are using a cell that do not reproduce the experimental XRD position of the, because what we did, we took one database from web that was a small cell, and so in that case, what they did, they took the position only of the iodine lead atoms that do not reproduce actually the XRD at room temperature. As you know, the organic part, what they do, they change a lot the angle. And if you do simulation without considering this, so you have to increase the cell, hollow to have the right angle, and then you can have some experiment. Because, for instance, in that paper, thanks to the referee, we obtained similar results theoretically, but the splitting was not in the conduction but in the valence. And so we interpreted it completely, probably wrong. I'm still convinced that what we did in the first version of the manuscript was not completely wrong. There are two effects. One due to this organic role, and the other one due to the splitting in the conduction. But this kind of stuff is very important when you have these materials that are not so simple like normal semiconductor. You know, this class of material like perovskite, comparison with experimental data, be sure that the experimental data and theoretical atomic position are in agreement is the first step. If not, you do the calculation and then you realize that the simulation gives you results that are wrong because the atomic structure is wrong.
What I see could be the main difference between the calculations and the experiment is about K, which is probably not a good quantum number in perovskites, because you have so many atoms that the disorder is huge. You already lose the goodness of K as a quantum number internally in semiconductors.
So this is something. No, I agree. I'm assuming that everything is crystalline and everything.
But when you compare with the experiment, it's maybe a major point.
Yeah.
May I ask maybe a silly question, but I'm not absolutely an expert on this. When we collaborate with theoreticians on STM measurements, we usually want to make a comparison with low temperature measurements because these are made at 0K. So what about the temperature here? Is it considered?
No, absolutely, it's really important. For instance, in the first class of material like TMD, if you go at low temperature or room temperature, you see that the peak change because in this material you do not have only exciton, you have trion. From this difference.
So
Timidity, this is a B exciton, this is a trion, because